Okay, so this is a review of chemical bonding. Compounds can be differentiated by their chemical and physical properties. Two major categories that we've talked about in the bonding unit are ionic and covalent compounds. Please remember that another word for covalent is molecular. They are synonymous. So a question might say which one of the following is molecular. Ionic compounds are formed when a metal combines with a nonmetal. And ionic compounds have ionic bonds. Remember, in ionic compounds there is a transfer of electrons specifically from one atom to another. When these electrons are transferred, we form two ions, a positive ion and a negative ion, and it's those opposite charges that make the two ions attracted to one another. In molecular compounds, we have a bond formed between two nonmetals. And molecular compounds have covalent bonds. So which of the following contains ionic bonds? Well, what you want to be doing here is looking for a metal and a nonmetal. And clearly, this is choice 3. Which formula represents an ionic compound? Here's another one. Clearly, we're looking for a metal and a nonmetal, and the best choice is 1. Chemical bonds are formed when valence electrons are A, either transferred from one atom to another, as in ionic bonds, or shared between atoms, as in covalent bonds, or just mobile within a metal. That's metallic bonding. We have metallic atoms immersed in a sea of electrons. Ionic bonds are formed when metals transfer their valence electrons to nonmetals. Remember, metals want to give up to form that octet, and nonmetals want to gain to form the octet. And as I said previously, those oppositely charged ions, the positive and negative, are attracted to one another and form an ionic bond. So here you see sodium with 1 valence electron and chlorine with 7. A very nice partnership. Sodium will give up its electron and chlorine will gain it. When that happens, remember that because sodium gave up an electron, it forms a positive ion. Because chlorine gained an electron, it forms a negative ion. And the brackets always go around the nonmetal. And you must use the charges to show how many electrons have either been lost or gained. Additional atoms may be necessary to ensure that all ions formed have a stable noble gas electron configuration. So let's look at what happens when aluminum combines with oxygen to make aluminum oxide. Well, you know aluminum's +3 and you know oxygen is -2. You are going to get Al2O3. So we have Al with a +3 charge, which means it wants to give up 3 electrons. And you have oxygen with a -2 charge. It wants to gain 2. So what happens is, when these drop and cross, this comes here, and this comes here, it gives you Al2O3. So what that tells you is that you need 2 aluminums and 3 oxygens in order to make this union work. And that should make sense, because if each Al, let's draw 2 more here, is going to give up 3, that's a total of 9.
If there's a student, Dejani Torres, in the building, please report to the main office. Again, Dejani Torres, please report to the main office.
That's a total of 9 electrons. Oops, I don't need. So here, sorry, 6. We're going to use these 2 down here. 6 electrons. And if I have oxygen, and I have 3 of them, and each one wants to gain 2, then this works out very nicely, because this is a total of 6 that it wants to gain, and this is a total of 6 it wants to lose. Okay, let's continue. Which species does not have a noble gas electron configuration? Remember, noble gas configuration is going to have a full octet. So if you look at Na, Na is number 11. When it loses an electron, it has 10 electrons, it's going to look like neon. If you look at magnesium, it's 2882. When it loses 2 electrons, it's going to be 288, a total of 18 electrons, which means it's going to look like argon. And argon already looks like argon, but sulfur is element number 16, and therefore it does not have a full octet. It has an electron configuration where it only has 6 valence electrons. So number 4 is your answer. This is back to aluminum. This is what I was showing you before. Aluminum wants to give up 3, and each oxygen wants to gain 2. So it takes a total of 3 aluminums and 2 oxygens. Let's look at some properties of ionic compounds versus molecular or covalent compounds. Remember, ionic compounds have a very high melting point. You cannot take salt, put it in a pan, and get it to melt. Why? Because it has ionic bonds. Electrolytes do not conduct electricity as solids, but do when dissolved or when molten. Remember that salt by itself will not conduct electricity. I did that demo for you. But if I take salt water and I put the probe in it, then the bulb will light. And it has no individual molecules. Now let's look at non-molecular or covalent. Low melting points and boiling points because there's weak attraction between molecules. Remember, it's either going to be LDFs, dipole-dipole, or hydrogen bonding. Ionic compounds or ionic bonds are much stronger than those type of forces. You can melt sugar in a pan on a stove. They're considered non-electrolytes. They do not conduct electricity as solids or when they're dissolved or molten. Remember sugar water? I had it in one of those beakers. It did not conduct electricity. Solids are soft and they form molecules. So this is the demonstration that I kind of did for you. The solution conducts electricity. Here's an ionic solid, salt dissolved in water, and the light bulb lights. Here, this might be sugar dissolved in water, a molecular solid, and it does not light. Which of the following solids has the highest melting point? So highest melting point, you're looking for something that's ionic, so you're looking for a metal and a nonmetal, which is going to be choice 2. Testing of an unknown solid shows that it has the properties listed below. Low melting point, so I'm going for something molecular or covalent. Nearly insoluble means it does not dissolve in water. It is a non-conductor. Therefore, again, probably molecular. And it's soft. So, nearly insoluble in water, non-conductor of electricity, and very soft. This is going to be covalent or molecular bonding, and it says, explain in terms of attractions between particles why the unknown solid has a low melting point. Low melting point equals weak attractions. High melting point would be strong attractions. It's all you have to tell me. So if this is molecular, it's going to have a low melting point and it's going to have weak attractions. Explain why the particles of this substance are non-conductors of electricity. Well, in order to conduct electricity, what do we need, people? We need mobile charge, and there is no mobile charge. There is no ions forming. Metals combine with nonmetals. They share electrons. The attraction of 2 atoms for a shared pair makes a covalent bond. Remember, electrons are always shared in pairs, and we always want to achieve 8, except for hydrogen, who only wants 2. So when you look at hydrogen chloride here, or hydrochloric acid is its other name, you can see that chlorine has 7, H has 1, nice little sharing. Chlorine has 8, hydrogen has 2. This is a polar molecule because remember, chlorine has a higher electronegativity than hydrogen. Water's got 6 valence electrons. H comes in on this side and this side. Remember, water is also polar because the oxygen has a higher electronegativity than the hydrogen. NH3, N's got 5, each H has 1, N now has 8, each H has 2. This is also polar. The pull in the east-west direction cancels out, so you have a net pull in the northern direction. So this is polar. And this is methane, or CH4. This is nonpolar by symmetry because the pull is equal and opposite. Which type of chemical bond is formed between two atoms of bromine? Two atoms of bromine means it's diatomic, it's part of Brinkelhoff, so it's going to be covalent. Nonpolar covalent, to be specific. In a multiple covalent bond, more than one pair of electrons are shared between two atoms. Here, when oxygen bonds with itself, it has 6 valence electrons. So if it bonds to another oxygen, it needs a double bond between it because it needs to pick up 2 more. Nitrogen, on the other hand, has 5 valence electrons. It needs to pick up 3 more in order to achieve its octet, so when it bonds to itself, it'll be via a triple bond. And CO2 is one that I stressed in class that you must know. It's linear in shape, and there's a double bond between each C and O, and it's nonpolar by symmetry. And it forms a double bond on each side so that the O's and the C's will all have 8 valence electrons when they're done sharing. So which molecule contains a triple covalent bond? Well, you know Cl's got 7, so if it bonds to itself, it's only going to be by 1 bond. You know oxygen has 6 valence. If it bonds to itself, it's got to do it by 2 bonds. And nitrogen has 5 valence electrons, so if it bonds to itself, it's got to do it by 3 bonds. So there's your triple bond. Molecular polarity can be determined by the shape of a molecule and the distribution of the charge. We call these shapes linear, bent, pyramidal, or tetrahedral. Linear just means that it's in a line. Bent is like water. A pyramid is like NH3 or PCl3 because you've got that lone pair of electrons on top. Tetrahedral is in 4 directions, so it looks like a cross. Remember, a polar molecule is called a dipole. It's going to have a positive and negative side because of the unequal charge distribution of the electrons. The atom with the higher electronegativity is going to have more pull and thus a slightly negative charge. Symmetrical or nonpolar molecules include CO2, CH4, and diatomic elements. Asymmetrical or polar molecules include HCl, NH3, and H2O. See how there is an unequal charge distribution. The element with the higher electronegativity is going to pull the electrons toward it. When an atom gains 1 or more electrons, it becomes a negative ion and its radius increases. When an atom loses 1 or more electrons, it becomes a positive ion and its radius decreases. Remember, when you gain weight, you become happy. Remember, when you gain weight, you become negative and you get bigger. So that's like nonmetals gaining electrons. They become negative and they get bigger. When you lose weight, you get smaller and you become positive. So that's like metals losing electrons, becoming smaller, and forming a positive ion. Compared to the radius of a chlorine atom, the radius of a chloride ion is what? Well, a chlorine atom and a chloride ion. Chlorine's a nonmetal, so it's going to gain. So the chloride ion is going to gain an electron, and when it gains an electron, it's going to get bigger. So choice 2. Which electron configuration is correct for a sodium ion? Not a sodium atom, but a sodium ion. A sodium atom is 281, but it's going to want to lose that electron, form a positive ion, and have the electron configuration 2,8, which will mimic neon, a noble gas. Given the equation, what's happening here? Well, you can see fluorine has 7 valence. When it gains an electron, it becomes a fluoride ion with a -1 charge. it gained, and when you gain, you get bigger. So a fluoride ion, which is larger in radius than a fluorine atom. When a bond is broken, energy is absorbed. When a bond is formed, energy is released. Remember, that window doesn't break by itself in the back of the room. It has to absorb energy from somewhere, either a body, a stapler, a rock. So when you break bonds, you need to absorb energy. When you make bonds, you release energy. Atoms attain a stable valence electron configuration by bonding with other atoms. Noble gases have stable valence configurations and tend not to bond. Physical properties of substances can be explained in terms of chemical bonds and intermolecular forces. These properties include conductivity, malleability, solubility, hardness, melting point, and boiling point. The stronger the intermolecular forces, the higher the boiling and melting points. So Ionic is the strongest, then molecules with hydrogen bonds, then dipole-dipole or polar bonds, and nonpolar with LDFs being the weakest. So let's look at this. You have 4 compounds and their boiling points. Which compound has the strongest intermolecular forces? Well, the one with the highest boiling point. So the highest boiling point is going to be a positive value, 19.4. Electron-dot diagrams, or Lewis structures, can represent the valence electron arrangement in elements, compounds, and ions. Here you just have the Lewis structure of an atom versus the Lewis structure of an ion, because fluorine will gain 1 electron, so therefore we need brackets and charge. A molecular compound, where there's just a sharing of electrons, no brackets, no charges, versus an ionic compound where there is a transfer of electrons from the metal to the nonmetal. So we have a positive ion, it gave up 1, a negative ion, fluorine gained 1. The positive and negative charges attract, and a bond is formed. Dots represent valence electrons. Everything else, the inner shell and the nucleus, is called the kernel, and we only represent that by the symbol. So phosphorus has 5 valence electrons, so we draw 5 dots. What is represented by the dots in a Lewis electron-dot diagram of an atom of an element in period 2? So if you're in period 2, it's going to represent the valence electrons in the atom. The correct order to fill in the dots to make a pair from the first 2 and then go round robin. The Regents really doesn't care if you don't follow this exactly, so long as you don't have more than 2 on one side. If I asked you to draw the Lewis dot structures of the first 18 elements, this is what it would look like. H, He, Li, Be, Bc, N, O, F, Ne, Na, Mg, Al, Si, P, O, Cl, Ar. Notice the elements in the same group have the same number of valence electrons. When metals lose electrons to form ions, they lose all their valence electrons. The Lewis dot structure of a metal ion has no dots. The charge indicates how many electrons were lost. So, if we form a magnesium ion, it means it gives up 2 electrons, and we only write Mg plus 2. We don't write anything else. So when nonmetals gain electrons, they fill up their valence shell with a complete octet, except hydrogen. The ion is then placed in brackets and a charge outside. So here you can see magnesium gave up 2, each fluorine took 1, So the fluorines are in brackets, each with a negative charge. And the formula is MgF2. So draw the Lewis structure for an atom of calcium. So calcium has 2 valence electrons, so Ca, 2 dots. Draw the electron structure for chlorine, Cl with 7 dots. Draw the electron-dot structure of calcium chloride. Well, you can see that chlorine only needs 1 more electron, but calcium wants to give up 2. So we're going to need another chlorine here. And that's what our final diagram would look like. Draw an electron-dot diagram for each of the following. Calcium oxide. Well, calcium is Ca, 2 electrons. Oxygen has got 6 valence electrons, so that's a 1-to-1 ratio. Ca gave up 2, oxygen gained 2. Hydrogen wants to give up 1, and bromine wants to gain 1. But they're 2 nonmetals, so they're only sharing. That means no brackets, no charge. Carbon dioxide is the special one. I told you there's a double bond in between the C and the O in order for each oxygen to have 8 and the carbon to have 8. Electronegativity indicates how strongly an atom of an element attracts electrons in a chemical bond. Fluorine has the highest value, 4.0. It's the bully of the periodic table. Nonmetals have a high electronegativity because they want to attract electrons, so they can fill their valence shell and have an octet. Metals have low electronegativity because they want to lose their electrons. They want to get rid of those 1 or 2 or 3 in their valence shell, so they have 8. The strength of an atom's attraction for electrons in a chemical bond is electronegativity. The electronegativity difference between 2 bonded atoms is used to assess the degree of polarity. Remember, polar covalent bonds form between 2 different nonmetals, one with a higher electronegativity than the other. The molecule with the higher electronegativity will have a partial negative side. The one with the lower electronegativity will have a partial positive side. The electrons are attracted more to the atom with the higher electronegativity, as I just said. So, most polar, you're going to look up the electronegativity difference. So H is the constant in all of these. So you just really have to look up which one of these, Br, Cl, F, and I, has the highest electronegativity. Well, we already know it's fluorine, because fluorine is the bully of the table. It's kind of in between the 2 and the 3, but it's the 3. So here's 3 types of bonds to review. Ionic, transfer of electrons between a metal and a nonmetal, must have brackets and charge. Polar bonds, unequal sharing, and that occurs between 2 different nonmetals, where one has a higher electronegativity than the other. Nonpolar bonds means there's equal sharing occurring between 2 of the same nonmetals. Or you can be nonpolar by symmetry. Metals tend to react with nonmetals to form ionic compounds, and nonmetals tend to react with other nonmetals to form molecular or covalent compounds. Ionic compounds containing polyatomic ions are said to have both ionic and covalent bonds. So here is table E with all of your polyatomic ions and their charges. A polyatomic ion is held together by covalent bonds. So it's covalent in here between the N and the H because they're nonmetals. But it's going to be ionic when it bonds to something else. Chlorine wants to gain 1 and NH4 wants to give up 1. So here's the ionic bond between the 2. The bonds holding metals together in their crystal lattice are called metallic bonds. All metals have metallic bonds. This is referred to as positive ions immersed in a sea of mobile electrons. Bonds are between kernels, leaving the valence electrons free to move from atom to atom, and that's what allows them to conduct electricity. So metallic bonding occurs between, you're looking for a metal, so that would be copper. The high electrical conductivity of metals is primarily due to, remember, in order to conduct, you need mobile charge, in this case, mobile electrons. Which substance contains metallic bonds? There's only one metal on the list, and that's mercury. A chemist performs the same tests on two homogeneous white crystalline solids, A and B. Look at the results. High melting point for A, low for B. Very soluble in water for A, not so soluble. A is a good conductor, B is not. Right away, we would know that A has got to be ionic. So, both solids contain only ionic bonds? No. Both solids contain covalent bonds? No. Solid A contains covalent? No. Or 4, solid A contains only, this is missing, it says ionic bonds. I don't know why this check mark is here. I think this slide is a little off, but A is definitely ionic and B is covalent. All right, so we got some things to do here. Each molecule listed below is formed by sharing of electrons. So we have Cl2 and Cl4. And molecule C is way over here, NH3. So draw the Lewis dot structure for NH3. Well, we've done that already. 5 electrons, 3 H's. Explain why CCl4 is classified as nonpolar. Well, if you draw CCl4, you'll have a C in the middle with 4 Cl's, north, south, east, west. So your electrons are distributed equally. It is symmetrical. Explain why NH3 has stronger intermolecular forces of attraction than Cl2. Well, NH3, remember, stronger intermolecular forces, we discussed this today. NH3 has hydrogen bonding, where Cl2 is nonpolar with LDFs. Explain how the bonding in KCl is different from the bonding in A, B, and C. Well, A, B, and C is all nonmetal.